good afternoon to all of you. So, I'm Biranchi Panda, an assistant professor at IIT Guwahati. Basically, I'm a mechanical engineer. So, I'm a mechanical engineer. So, my purpose of doing concrete printing started when I joined my PhD program at Singapore. So, today I'm very happy to share some of my research activity when I was doing at my PhD level, and also I'm going to share some of my research, what I'm currently doing in India for 3D printing of concrete. Okay, so thanks to my colleagues who have invited me to give me the opportunity to discuss these ideas with you. So with these background informations, I would like to start the research journey. So basically, this is the content of my presentation. So I want to start with the technology called 3D concrete printing, which is a part of digital concrete construction. And then, of course, when the machine is there, then we have to deal with the various materials. In this regard, I want to talk more about the material rheology that is very important when we want to deal with 3D concrete printing. And especially when we have a better material, better machine, it's important to connect them together. So therefore, in knowing the process property relationship is also very important. So in that regard, we want to discuss some of the key findings from our research group, that we have seen that in fact, if you have a good material and machine, it is very important to connect them properly. So that is the third content. And towards the end, when we have a system, when we have a material and a good process property relationship, we went for some industrial project. So that's all I want to highlight in this topic. So without wasting much time, I would like to jump into the concept called digital constructions. So of course, everyone know what is a traditional construction process. We used to create a mold for creating the structures. And as you can see in this picture, when this happens, we need a lot of formwork, molds to create the structure. After the structure hardens, we again have to remove it. Literature says that when we are involving in such kind of traditional based construction process, it incurs a lot of cost, time, and also the labor. You can see easily from this picture I am presenting here. But if I see the other side, it is also mentioned that in terms of industrial growth, the impact or the productivity of this construction industry is quite stable over the years. Okay, so in the graph, it is referred that if you see some manufacturing, agriculture, business, it is being mostly automated and digitalized, and thereby it is increasing the productivity. And for construction sector, one of the reasons can be considered the lack of automation, which is causing a very stable productivity over the years. So our construction industry is a very huge platform. You can see that it is about $10 trillion industry. But if you see some of the projects that are 20% over time, and some projects are 80% more costly. So in this regard, like, it also contributes to 6% global GDP. And in this regard, it is very important to see how people are involving in this kind of traditional way of constructions. They are risking their life into different environment. So what is the positive message coming out from this picture? That if we can come up with an automation technology or a strategy to completely digitalize the building fabrication, at least these workers will lead to a better life. Okay, and secondly, the productivity issue that just now we've seen from a pictorial representation, there is a possibility we can also improve the productivity by bringing such kind of automated machine to our construction industry. For me, printing of concrete, having some few reasons, but to be very specific, the first reason is all about design freedom. Because if you have seen that when we are going for a traditional way of creating structure, we need the mold, formwork, and you imagine that when the structure is going to be more complicated, complex, the amount of formwork, the mold that you need, it's again going to be huge. And also it is going to be cost, it's not going to be affordable anymore when you want to have a unique design by an architect. So in that regard, I will give more points to concrete 3D printing, because in front of you, there is a very good example. It is done by X3. They have printed a coral reef, which is of any complex design, and this has been 3D printed without the need of mold. So that is the first advantage we get when we want to print something without the need of mold. That we have a machine, that we have a robot, it can be of gantry, but without the need of mold, we are depositing the concrete layer by layer, which happens in extrusion-based 3D printing, and doing so, you can create more complicated geometry that do not require any kind of mold or form work. The second reason, which is very close to my heart, is all about sustainability. We always deal, as a civil engineer, we always talk about sustainability in terms of using some industrial waste as a supplementary cementitious materials along with cement. But what extra added advantage you get when you deal with 3D printing is the design sustainability or structure sustainability. In front of you, there is an example of 3D printed bridge in Netherlands, and surprisingly, if you see the cross section of the bridge, it is not entirely solid one. Rather, the topology has been optimized to minimize the concrete uses. So it means that now if I have a 3D printer and I want to design some structure, I have an opportunity to optimize the design in such a way that I can use less concrete. So it is also one possible way to increase the sustainability in our complete building design, that instead of dumping all the concrete inside a complete rectangular or any shape of formwork, I have the freedom to design a lattice design or maybe topological optimized design that is going to save a lot of concrete, and it is also going to affect the sustainability index of my fabrication process. Usually, the extrusion-based 3D printing often started with depositing of fresh concrete layer by layer, as you can see. But we also have another process called D-shape or particle bed fusion, where you can also, I think there's a video, you can see that here we have a machine that drops the binder in a predefined path so that it is going to hold the loose sand together. And by doing so, you can also create a complicated geometry out of a particle bed which contains most commonly sand. Okay, of course, there are some research, you can change the material, you can change the binder, but the concept remains same, that you have a bulk of sand and through layer by layer deposition, you are selectively depositing this binder that's going to hold the shape. And ultimately, once it is completely solidified, then you are going to end up with such kind of designs. So you can also print a very complicated coral design. So you can see it's a machine that is depositing this kind of binder material selectively, and ultimately when the printing is completed, you can remove these loose particles, and at the end result you will get a complicated geometry that is bonded together as a result of binding activity of the binding material. So this is somehow comes under concrete printing category. There are many different digital processes that also in construction process. Some of the contribution from ETH during smart dynamic casting, you can see that if I want to automate a fabrication process of a completely concrete pillar of adaptive shape. So here is an example of robot that have a mouth opening, it can adjust to the shape, and accordingly you are going to create a more beautifully designed column. And similarly, we have mesh molding robot which are helping the construction industry to do many jobs in a more automated way. But as also some, you might have seen some examples in the YouTube regarding robot bricklaying machines. So our construction industry, we have some machines to automate the process. But coming to this robotic 3D printing or concrete 3D printing, the idea is not actually a new idea, because I have a video for you. You can see that
on October 20th, 19.
It's almost long, very old video, and in this video they are showcasing
for a wall building machine. The person most of whose time was devoted to the invention of equipment for the food industry is the author of the first building 3D printer. He created a prototype.
Yeah, so you might have heard him that saying that this is invention is more about a machine that deposits the material. It may not be concrete, it may be earth material, it may be something different, but the idea or the principle remains same, that with the help of machine, you are depositing the material layer by layer, coming up to a complete 3D structure. Okay, so
October 20th, 19.
Then Episcore or other companies, they came into the picture. They also claim that no, they can print this entire house in one day of time. So you can see they have a more advanced machine that I imagine that nowadays when we are talking about concrete printing, though the principle remains same, we are advanced more in terms of the machine, that we have more degree of freedoms. The robot can deposit in many different directions. We have multiple robots, can put reinforcement, can do plastering. So in terms of machinery, we have done a lot of advancement, but the idea, it remains, it's an old idea, I will rather say, because there is proof that in the early days, the similar kind of machine was used to deposit some material in the layer by layer manner. Okay, again, there is a very good example that Professor Kushnabis, he also presented the idea of contour crafting. This concrete printing also somehow it is being connected with this idea, that he put a concept for printing this kind of habitat in the Mars for the astronauts. So the idea was that someday robot will go to the place in a space, and like using the local materials, they are going to deposit the material layer by layer, which is going to create an habitat for them. So it's again an automated way of constructing habitat. The similar concepts can brought down to earth to do some kind of research. So when I joined PhD, you can see from the graph that how exponentially the interest in concrete printing rise up. It is from both academia as well as from industry. They put more attention toward the technology, and somehow today we can see many more examples of concrete printing in the world. Okay, so I have one printing video snapshot. So you can see that this is the machine I used in my PhD. I have a quick video. You can see how the material deposition takes place in concrete printing. So we have a rotating nozzle, and it is rotating when we have some turning and corners around this design, and we are depositing fresh concrete. I will not say concrete because, I mean, from civil engineering perspective, it is a wrong to say concrete. Rather, we are using a mortar, because of the restriction in the nozzle area, we are still using fine sand as an ingredient. So I will not call concrete, but like in general, people say concrete 3D printing. So the flow is in that way, but rather I will say it is mostly mortar 3D printing. The mortar is being printed layer by layer. The machine is capable of depositing this material as per the predefined path planning. So this is the gantry version of a 3D printer. You have mostly people call gantry 3D printing. So you can see that we have a 4-axis machine. The 3-axis refers to X, Y, Z, and 1 axis is all about rotating, that you have seen in the video, that when the turning comes, it is keep on rotating. So that is the 4th axis we have in this machine. On the left hand side, you can see a control box that is controlling the entire machine, and right hand side you can see a pump. So we have the nozzle, you can see, and this pump and the nozzle are connected with a hose pipe. So when we operate the pump, the material from the pump, it goes to the print head, and then we deposit it layer by layer. The whole machine is controlled by this control box, where we start with a 3D CAD model, create the G code, and put in the machine. This machine SSC NC controller, it accepts the G code, and accordingly design the path for 3D printing. So this is the typical flow of concrete 3D printing based on a gantry system. So we also had a robotic system. It's a 6-axis KUKA robot system. We integrated the nozzle. As you can see, the blue color pipe, that is the hose pipe. It is connected with the nozzle or the print head to the pump. So we can pump the materials to this exactly the print head point for deposition of the concrete. So using this RoboMaster, sometimes we do the path planning. So you can see that if you want to print a design, then you can easily do the path planning. Of course, robotic programming are not that complicated. If you have the proper planning algorithms or the softwares with you, you can properly. Initially, we had an issue of slowing down in the corner, but later we solved it. So now for every printing, the printing is the printer head is moving with a constant space. So you can see, previously we used to slow down the speed in the corner, but later we had some issue with the pump, and then you can see now it is being slowing down and the corner. And then but the problem what you can see here, that when we are slowing down the robot speed, as a result of that, we have to also control the pumping speed, because both have to run synchronously. If you somehow decrease the robotic printing speed, you have to also manage the pumping flow rate. Otherwise, material over depositions may take place. So now, since we are talking about material, let me highlight some key aspects of material that are important for concrete printing. So, of course, those who are from civil engineering, they can easily identify when you mix this mortar, we take cement, sand. The starting material can be cement, Portland cement, sand. Of course, we don't carry stones now, water and some admixtures. If you see the materials that we need for 3D printing of concrete, of course, we do not need a very low stress material, because in that case, no, the material is simply going to flow away once you deposit on the print board. We have a printing board, and if you deposit a material of very low yield stress, then it is simply going to flow away. And then in another way, if I want to try with a very high viscosity material, then of course I can print stable layers, but they cannot be printed in a continuous manner. So you can see a lot of discontinuity. So as a result of that, this is a very good schematic I referred from a paper. So you can see that they presented that for concrete 3D printing, we need to maintain some minimum yield stress. And slowly, if you want to targeting a large scale printing, then the material structural built up, it must be rapidly increasing with time, because if that is not happening, then of course you are going to end up with strength based failure. I will show you some videos from my lab that how we can see some strength based failure if the yield stress or the structural build up is not happening rapidly. Okay, in other way, if you are making a concrete of rapid set and not depositing the second layer, because normally when you print layer by layer, you have some time gap between these two layers. If the time gap is very huge, suppose I'm printing one layer and allowing 20 minutes, 30 minutes time for another layer to be deposited. And in that way, if my yield stress is rapidly increasing, then I may end up with poor bonding strength. Okay, so this is the failure we can see. So when you are not improving or increasing the structural build-up of your material, you are going to end up with this kind of failure. And if you are having a material which is having very quick setting time and you are delaying the print time gap between these layers, you may end up with poor bond strength between the layers. So how to manage these two things? So normally we rely on a concept of texturotropy. So what is texturotropy? So normally when we squeeze a paste from the tube of a toothpaste, so we can easily see that when we apply shear force, this paste can comes out of the tube easily without any deformation, and then without any application of the force, it remains stable on the brush. So similar behavior we need in 3D printing. So when we want to apply some shear force, material should be extrudable, but when we remove the shear force, material should remain its own position. So this is the two contradicting criteria we have to fulfill in concrete printing, because if you remember the process very well, then you can imagine that first you have to pump the materials. The material have to come from the pump to the print head. So in that regard, the material have to be very fluid enough. So otherwise, it is going to create some clogging. But once you deposit on the print bed, the material must have some property to remain stable, because if you simply print that pumpable material, it's not going to be stable. And if you make a very steep material, considering the fact that I want a stable filament, then you may have some difficulty in the pumping. So these two contradicting criteria you have to fulfill when you are designing the material for concrete printing. So how it happens normally, if you take the Portland cement, so it has a texturotropic property. So the texturotropic means like when you apply shear force, it will decrease and the viscosity will go down. And when you remove the shear force, it has the ability to recover back. So it happens, it's an inherent property of Portland cement based mix. So as you can see this, you can refer this paper of Nicholas Rosen. So he already clearly explained that, you know, when cement particles, they grow with time, the CSS, they try to bond the cement grains, and, you know, progressive time, more CSS will form and they will try to hold this particle. And what is happening, you can see that they have some inter-bonding, and these bonds are very poor. I mean, with application of shear force, you can easily break that. And due to flocculation of these cement particles, even if you break by applying some shear force, and you can easily decrease the viscosity for pumping. But once you remove the shear force from the pumping side, then this material have a flocculation ability. It will reflocculate and it will gain the same yield stress or almost 80 to 90% as of before, so that you will get a stable filament. So this is a very brief scientific background of how to design the material. You have to rely on the texturotropic concept. So, but what we intended to do, we wanted to replace the Portland cement with some kind of industrial waste like fly ash, slag, okay, because we want to have some sustainable material at our end. And in that regard, we feel that when the spherical particles you are using a huge volume, maybe 60% replacement, then it is decreasing the yield stress. And ultimately, what is happening after printing a few layers, again the layers are slumping, you are end up with collapsing of the layers. So this is what we observe in the beginning, that when we want to add a lot of industrial waste, so we are not getting a stable print quality. I mean, not a stable buildability. We can't print after than 10, 20 layers. So in that regard, what we did, so we can see continuous failure of our designs. We added some kind of nanoclay to improve the yield stress. There are different ways to increase the yield stress, but we have to consider the fact that just by increasing the yield stress without keeping the flocculation concept, it may end up with a very stiff mix, which will be difficult for pumping. So therefore, we selected nanoclay. Again, there are different clay and there are different mechanisms how it affects the improvement of the yield stress. So you can see just by adding 0.5% the nanoclay to the mix, that the high volume fly ash mix I have shown in the previous slide, we were able to improve the yield stress significantly. And there are some reasons behind that. And as I told you, there are so many clays are available with us, and all the clays, they react to the material in a different way. But the nanoclay we used in this regard, it actually helped in getting more flocculation, which is good for 3D printing, because if you get a yield stress by flocculation mechanism, it bring down the viscosity when you apply shear force. There are many ways. People used to add a lot of fibers to it. Some people, they try to decrease the water to binder ratio, trying to make it more stiff mix. But ultimately, they may get the stable filament. But the main issue they will face on pumping. Those who are pumping the concrete, pumping steep mix is very challenging. So therefore, there are different way to improve the stiffness or the yield stress of the material. Okay, so that have to be considered properly, because we have to consider this fact that we are anyway going to pump this material. So when you're going to pump this material, we should not cross certain limit of yield stress, or else then pumping will be very difficult for us. So with this improved material, so we are able to print more layers without any deformations. We could have gone up to more number of layers, but then we jumped to another idea of measuring the deformation in the layer. So in that regard, what we did, we attached a laser distance sensor to our nozzle, and with that we try to measure the deformation of each layer. It is very useful information, because when we are printing, somehow the layers will be deformed, and if the deformation continues, then what is going to happen? Then these layers are going to be collapsed at some point of time. So to avoid that, we try to measure the deformation of the layer through this laser distance sensor unit. So it actually measures the deformation of the layer in during the printing process. And our idea was that once we collect the data, we are going to analyze it and then optimize it based on some AI algorithm. Then this was the plan. That's why we added some kind of laser distance sensor unit, and we did it. And second thing is that when we wanted to bring some new material design for this 3D printing applications, we always do this kind of texturotropic characterization. It is very important, because we are discussing about texturotropic property. So we must know that how this texturotropy affects the final result. And in that regard, we do shear thinning and viscosity recovery test. You can see from the screen that when we apply shearing action, viscosity, which results in of the Isotropic test, and based on that, we keep on adding more layers. In this way, we keep on adding more layers. So we also do some research on different geopolymer printing. So here is an example that we participated in a NASA competitions to print geopolymer. So the idea was to print with a small robot. So we have developed a geopolymer material which is printable, and we have demonstrated in such a way that you can see in this video that the idea was to not having any small deformation during printing. So we put a scale bar next to the printer, and during printing we try to see that after printing of 30 layers, are we getting any deformation, yes or no? So in that regard, you can see from this video, let me play for it. Okay, for you, yeah. So you can see this in this video, we are trying to print a geopolymer. And then the printing process can be considered as more robust. So you can see that we are printing this layer by layer using a small robotic arm. The robot pipe with a pump.
Dr. Biranchi, sorry.
Yeah, I'm here. Yeah, I just wanted to show this video so that you can see that after printing of this kind of layers, we are not having any deformation in the material. So anyway, so I am moving to the next slide. So you can see that these are the materials we normally use for making the geopolymer, and we also very much cautious about the viscosity of the potassium silicate that we use in activator. So you can see that for different molar ratio of activator, we are going to end up with different viscosity, and as a result of that, we can see that different materials are coming with different yield stress and viscosity. So what is the main conclusion we are getting it here, that in case of geopolymer, the activator or the potassium silicate viscosity plays a bigger role on controlling the viscosity and yield stress of your final mix. So you can see that I have 1.8, 2.0 different molar ratio, and with respect to different molar ratio silicate, we are having different viscosity, which is controlling the viscosity of the mortar, and as a result, we are getting two different print quality, as you can see very clearly from the screen. So sometimes we get standup distance. So if the material is slumping with time, we'll get some standup distance, and if there is no slumping, we'll get a very good printability. You can see that this is a old geopolymer, and we modified using some chemical admixtures, and you can see that there is no deformation during printing of the same design. Previously it was slumping. You can see there is an indication of stand-up distance. So it means slowly if you print, the entire structure is going to collapse. So sometimes we play with different designs to see how far we can print with our new materials, and sometimes we try also with some kind of overhanging features. So again, we have done some green strain measurement test to quantify the printability. So this kind of green strain, also with help of some direct shear test, we have done some kind of testing to quantify the printability, and we have done some modeling work with the help of some RMIT university students. So now we can model the printability in a more appropriate way. So you can see that whatever printing we do, now we have a model. It is going to capture it properly so that we can see the early deformation, and accordingly we can create a new mix design. So
I'm sorry, Dr. Biranchi.
I think
Can you hear me?
Yeah, I can hear. Yes.
You have a few minutes left, so if you can just explain briefly, we would be so thankful.
Yeah, I think that's the end of my this presentation. I think this is how we have moved into different printing structures. Okay, so towards the end, I just wanted to share some of my experience in printing large scale designs. So with this material development, we have printed large scale structures, that bathroom units. We have done some kind of furniture printing. And at IIT Guwahati also, we are exploring some kind of new material design along with topology optimization structures. So this is the research content from my side. So thank you very much for the invitations. I would like to take some questions. If you have any doubt, I'll be happy to discuss it now.
Thank you so much for your time. We appreciate it. And I'm asking the audience if they have any questions on the topic. And the guests that we have online, the participants, do you have any questions towards Dr. Biranchi?
Yes,
yes, I have a question. I raised my hand.
Yeah, please. Yeah.
Okay.
Yeah, Mr. Biranchi, I would like to know if this work or this 3D printing work can be done in real life or in a bigger scale. Can it be applied in reality? Because we already have 3D printing by plastic and other materials, but can it be done in concrete in real life and bigger sizes?
Yeah, it's a very good question. Actually, there are some projects who have done in a large scale. You can find company like COBOD, COBOD, and company like COIPE. They have done this concrete printing large scale. But coming to your second question, that we are still limited ourselves to mortar. There are some research group, they are trying to bring large aggregate to print real concrete, because so far whatever I have presented and whole world is doing, it's all about mortar printing. But soon I hope there are some research group who are working to bring large aggregate to make like a more concrete kind of feeling. So soon I hope there is a possibility we can print real concrete for large scale printing projects.
Okay, but this printing process, as I saw in the video presentation of you, I saw it making like a spring shape, but can we eliminate that spring shape in the structure?
Yeah, possible. So, I mean, that kind of improvement we can do, like we can add some kind of design to the nozzle so that when you are printing it, you will get a very smooth surface finish. So there are some examples, because it is, you can see that by default, you will get some surface pattern because of the layer by layer printing. But if you want to avoid that, you want to get a better surface finish, it is possible to have some kind of surface layering kind of nozzle where you can clear all the extra material and you can smoothen the surface like we do in a regular construction. That is possible. I have seen some printing video. They have added some kind of flap to the nozzle to make it smoothen.
Thank you so much.
Thank you very much.
Is there any question here?
Thank you.
Is there any question?
Thank you very much, Dr. Biranchi, for this interesting and useful and it's a wonderful presentation.
Thank you.
Nizar from Architecture Department at IIT Guwahati. Of course, we have this is linked too much to architecture work. That's why it's very interesting. We hear about 3D printing and whether in labs or reality is a fact, and it will be soon probably applied in all the construction sites. But normally we see dealing with solid walls. There are many challenges in construction, as we know. And probably I will just talk about two of them. The first is, what about the reinforced concrete? For example, when we talk about ceiling or slabs, let's say, what's the procedure? Is there any practice about that? How to deal with reinforced concrete? The second thing is sometimes we, for the purpose of dealing with the thermal insulation, we use some kind of insulation, whether using the classic hollow concrete or we use, for example, bricks or cavity wall, let's say, in general. So what's the solution that 3D printing presents for solving this kind of things? Is there any practices? Are there any practices happening in this regard? If you can give us some information, I'll be thankful. Thank you very much.
Yeah, thank you very much. Actually, because of some internet problem, I could not hear you properly. But actually, I heard the reinforcement things. So especially now we are trying to print and we are applying the reinforcement manually. Suppose we are printing it, definitely we are not able to print with reinforcement. So what we are trying to do, there are so many examples where you can put the reinforcement with the material. There are some examples where the steel cables, people are extruding with the material itself to make it more ductile. And there are some examples like normally how we put in a regular constructions. After printing the lattice walls, they are trying to put the rebars in a more manual way. So that is what currently being done. Of course, as I agree with you that they need to put more attention on the reinforcement strategy. That only, I mean, this topic of concrete printing can be used for many structural applications. So this kind of research is still lacking. People are doing this kind of research now. They are trying to bring more structural aspect to concrete printing. And again, the good thing about is all about architect things. So that's what I heard from your side, that reinforcement. And due to some network problem, I could not hear you properly. So I request you to kindly drop an email. We can have some discussions separately. Thank you.
Thank you so much, Dr. Biranchi. And
Thank you so much, Dr. Biranchi. Actually, I had a question regarding the durability of these materials. How is there any relation with the normal conventional concrete that has been made and the durability of concrete used for 3D printing material? How the durability issues has been solved? Can you give us some clues? Thank you so much.
Yeah, durability is also an emerging topic now in concrete 3D printing. So initially the idea was to print concrete. So many research groups, they put all the interest to first make the material printable. But now it's not a big deal to print concrete. People are moving their attentions towards more that common issue, like one of the colleagues, he mentioned about reinforcement. Now you asked about durability. So slowly people are trying their attention to work on this topic. I have not seen many papers, but there are a few good papers on the durability. But again, what is the conclusion I have seen from the paper is all about how you print it. If you print it with a proper setting, with a proper microstructure packing, then the durability issue is not there. But there are some bad printing examples where due to the printing, you may end up with a lot of porosity in the sample. And that is causing very durability issue when you are recommending this kind of printing for any application. So there are good things, there are bad things. It all depends on how you are printing the material, what material you are using. So all these things can be considered when we have to talk about durability. But as I told you, not much research has been done in this regard. There are ample research scope is there on this topic. I hope we can continue this kind of work, because already printing of concrete has been in public domain. Now the shift is towards more durability, structural testing, getting standards, codes. So those things are still lacking. So we are now putting a lot of effort to bring standards for testing this rheology of the material for 3D printing, testing the mechanical properties, durability, reinforcement. So those are some key challenges that still need to be addressed.